the chance for misperception here. So ratio control in broad strokes has a very obvious kind of application. I think everybody here has been doing reactor design, and you can kind of think of a CSTR kind of application where I have A plus 2B goes to C in my reactor, okay? And if I'm trying to do my job, I want to feed those reagents in some specified ratio. And I think if you just think of those reactors as being blocks on a diagram, it's easy to make the mistake of imagining that what you should be doing is to simply feed these reagents in the correct stoichiometric ratio so that you get the correct output result out, right? And then feed at a rate which corresponds with the maximum reaction rate or conversion for the reaction. And I think we spend a lot of time doing those calculations. And so it can appear that ratio control is the perfect solution to this. Now there's a little bit of obviously subtlety here because reactions happen in molar ratios. So the stoichiometry is specified in molar ratios, but flow control typically happens. It's a lot easier to measure volumetric flow rates than to measure molar flow rates, and so quite often there's a couple of conversion factors that you had to take into account, but like once you boil all of that down and you've done all your unit conversion, you can kind of say, well, I know from back calculating from a ratio of 1 to 2 on A to B, that means I need like a ratio of 4.32 cubic meters of A per second to 1 cubic meter of B, say, right? Like these things can happen. And the simplest mechanical version of ratio control is, now I think you have to kind of take into account a lot of our previous discussion to kind of understand the exact configuration that we have here. But this is a very mechanically simple setup. When I say mechanically simple, it has a small number of components. In fact, it has the minimal number of final control elements. In other words, we are using exactly one valve. We are using exactly one flow measurement. And with the diagram that I've drawn here, we are using a very small number of computational units. So what we're basically doing, and you can draw this a couple of ways. You can draw a version like of this, which is even simpler, where that ratio is actually just implemented by a multiplication factor, which is kind of built into a gain unit, right? So you can basically imagine, I've drawn it here in such a way so that you could, it implies that there may be a knob somewhere that you could turn to kind of set the ratio. But obviously if you could conceivably just build a thing that just takes that signal, multiplies it by 5 and like writes it down to the... Now, again, I'm going to speak about, because I think the basic idea is pretty clear, right? Like I measure the flow and I manipulate the valve to obtain some kind of ratio. I think that high-level idea is very easy. But I want you to be aware of the pitfalls, and the textbook doesn't actually call them pitfalls, it just goes through these calculations as though it's relatively obvious. But I think the most important thing that you have to understand is even if you ignore all the mechanics, even if you ignore how exactly the flow is being measured and how exactly the valve works and all of that stuff, I think it should be obvious to everybody that the units conceptually of like a flow are not commensurate with anything that I can imagine actually sending to an actual valve. Right? So if that flow transmitter is measuring a flow, I can't just multiply by 5 straight up to get like a new flow which is 5 times bigger and then just write that signal directly to the valve, because what the valve is getting is something like a valve opening or a pressure signal or something like that. So obviously there's actually a whole lot of, like if we zoom into the mechanics here, right, remember that there are actual things that are doing the things that are represented by these icons. In other words, there is perhaps like an orifice plate in the actual line, which is actually, and these things that I've drawn over here are typically what you've seen this kind of notation before, and what that represents is physical taps. In other words, holes upstream and downstream from the orifice plate, which are connected directly to the flow and therefore have a pressure drop over them. And this thing that I've labeled FT over here will typically actually be a differential pressure sensor. Right? And so the difficulty comes from actually picturing the actual way that this stuff will work, because if that is a real orifice plate, and if that transmitter is actually measuring a pressure difference, then we have to remember that in broad strokes, most of the time, flow is actually proportional to the square root of the pressure drop. Right? So you saw this in CIO when you were doing piping design. Zoom up out of those equations that you've memorized, right? Think about the equations that you know for pressure drop over orifices, or pressure drop over a valve, or even pressure drop over long stretches of pipe. And you will see that they all have exactly this form. So for laminar flow, typically this relationship is linear, but for turbulent flow, which most of the time is what we have these square root relationships. This shouldn't surprise anybody. If you zoom out far enough, that's what you're left with. Now, I forgive you for kind of not having seen that, because you've been very preoccupied with memorizing the useful equations that can help you solve the actual problems that you do. But from a high level, you have to kind of just understand the shape, right? And so this is why you'll see in the book that some of these diagrams have a square root element over here. Why? Because they're making these assumptions, right? They're saying, okay, well, we're probably measuring the flow using an orifice plate. What's actually coming out of that orifice plate is actually a pressure difference. If we want to get something that is actually proportional to flow, we need to take the square root of that thing. Right? And so, again, it's the actual mechanics. Once you understand this, the actual stuff in the book becomes a lot more clear. I think they assume that you have perhaps internalized more of your piping design in kind of this intuitive way, because it should make sense reading that. Oh, well, yes, I kind of see what they mean. It is relatively common to see this kind of setup because it is cheap and because it's relatively straightforward to have just the flow measurement on the one side and the valve on the other side. Now, okay, so that's the first part that you have to understand, is that there's kind of a lot going on here, right? So all of this stuff, which conceptually ends over there, that's all the stuff that we need to kind of have a flow over there. But when I say flow, remember, the signal is actually carried by a wire, which means that it's not actually a flow. There's no signal saying 2.4 cubic meters per second. There's a signal saying 12.3 milliamps. And so there's a conversion factor there, which includes encoding in that electronic signal over there a flow to milliamps. And that's probably the only way that I'm going to multiply by something. Now, okay, when I say probably, right now it's probably the case that, like, if you want to multiply a signal by a number, you're going to do it using an electronic device. But, of course, back in the day, you can actually kind of imagine all of that being completely mechanical. So all of the stuff that I've drawn over here, especially the way that I've drawn it, in other words, if there's a pressure drop between 2 points, you can use that pressure drop to move something. Right? And if you can move something, you can attach that point that's moving to a lever, which will multiply it by something. And then you can attach the other end of that lever to a valve, which is mechanically moving up and down. Or, not only can you attach it to a valve kind of directly, but if you have some space where there's pressure available, if you have all the machinery that's generating all of this kind of signal air, you can have that mechanical linkage that I showed you when I showed you how the mechanical position controller works, right? Where that mechanical position controller was actually changing a pressure in the valve. And so the whole thing could conceivably be, this whole scheme could conceivably be completely mechanical. There's nothing in what I've drawn here that absolutely requires electricity of any kind. Electrons, like, do not have to feature into this. So it's only once you make those assumptions where you say, okay, I'm probably going to use electrons, I'm probably going to use an analog equipment, or I'm going to use a digital equipment. Every time you have to move from one kind of form of energy to another, there's a transducer. The transducer has a gain associated with it, right? Because at the very least, it's moving from one unit to another, right? And once you really have internalized that, once you have understood that, wait, every time, if there's a flow over there and there's a pressure over there, I need a transducer, I need something to convert between those units, then a lot of those examples start making a lot more sense. Now, okay, so that's let's say the specifics of this whole setup. That's the mechanics, right? The mechanics are, at the minimum, I need some kind of piece of machinery that measures one of the flows, at the minimum. And at the minimum, I need some piece of machinery that manipulates the other flow. Something that is also not always 100% clear to people is why this is feed-forward control. And you'll see that some of the examples in the textbook actually resemble feedback control a lot more than this scheme. But I think it's really easy in this scheme to understand that the so it's because the manipulation doesn't affect the thing that we're measuring. Remember, we're measuring stream A, but we're manipulating stream B. And nothing we do to stream B will ever change stream A. In fact, it's quite important to remind yourself, yes, We may have a little bit of time. Nice. Those are coming on. Nice. It's worth reminding yourself that this does not actually ensure that I obtain the correct ratio pretty much ever, given what we know about the way that plants work. And the reason why I'm saying this is because the reason why we are doing this whole thing in the first place is because we suspect that the one stream will change from whatever the value was that we designed it to be. Otherwise, we wouldn't have this scheme in the first place, right? Like, why would we have this ratio control scheme if we could rely on the flow rate of A not changing? The only reason why it is the way that it is because we suspect this stream is wild. It's going to change, right? Now, what do we know? So think about the graph, right? Where, and let's imagine, like, just to keep things really simple, I'm gonna draw a sketch here with time and flow, right? And this is like A and B flow rate, both of them. So close, it was right there. Oh wait, no, it's just moved. It just magically has moved to a different output. That's fine. Okay, cool. So imagine now we are attempting to do a 1-to-1 ratio. Just exactly, we're trying to, and then in this version of the thing, if you think about a 1-to-1 ratio, it becomes exactly like a kind of feedback control problem, right? Because we're trying to keep B on A, and so A is like a set point, and B is like the thing that we're trying to keep on that value. And so if you kind of leverage what we know already about control, about any kind of control that you can think of, it should become clear that if F is maybe doing things like this, right? Even in the best case, even with really good control, right? So if that's A, say, right? A. Even with good control, B will be doing things like this. Like even in the absolute best, like if that's a well-tuned controller and it's actually reaching the set point eventually and so on, B must be at least lagging behind F. Right? Like it can't be different because I'm measuring and the valve has dynamics and stuff, like all of these elements have dynamics, and so even in the best case, if it's a realizable kind of controller, the best thing is that B will always just be a little bit behind. But what behind means is that for almost all of the time, if I zoom in on a thing here, at every one of these times, B and A are not the same. Which means that at every one of those times, which are, if A is moving a lot, pretty much all of the times, right? I'm not actually feeding A and B in a 1-to-1 ratio. I'm trying, but most of the time I'm not succeeding. Okay, so that's the first big thing that you have to understand about this idea that even in the best case, even if everything is working exactly the way that it is, and like I've got a great model, and like the multiplication factor is fine, and there's no weird nonlinearity in my valve, and everything is perfect, the best I can do is something like this. Which means that almost all of the time I'm not actually getting that ratio. The second thing you have to understand is it won't even be as good as this. Why? Because that looks like I'm actually measuring, I'm actually knowing what the flow rate of B is so that I can do the micro adjustments that I need to do in order to get the flows to match up exactly. But that's not what's happening, remember? I'm just measuring the flow rate and then I'm setting the valve to some kind of fixed position based on just that measurement of the flow rate. I don't, in fact, in this scheme, even know what the flow rate of B is, because I'm not measuring. And so what does that mean? It means that the control will be significantly worse than I've sketched it over here. Now, what's the big take home of all of that? Is that you cannot rely on ratio controllers to obtain a ratio. Like if you rely on getting an actual exact ratio into your reactor, you cannot do it using ratio. Okay? So what ratio? So why do we have ratio control then? Because ratio control is right up front, and it's a really great way to minimize the effect of deviations in those flow rates on the eventual. So like we're trying to get it as small as we can, but so we can't get it exactly what we want. We're trying to get it as close as we can. The second thing that I want you to understand about ratio control, and this is straight up, this is not even like, oh, someday in industry you'll realize this. Like literally next semester, many of you will have forgotten this lecture and you will be docked marks for doing the following very silly thing. And that is, you will calculate in your final year design a desired ratio for your reactor. You will go to a great deal of effort to find the perfect operating position for your reactor. You will characterize the temperature, the pressure, and the amount of all of the reagents that are necessary to get optimal conversion of your product in your reactor. And then you will design a control system to make that happen, which is completely wrong. Does everybody understand why it is completely wrong? May I remind you of our first lecture? Operating at design conditions will not result in the designed outputs. Right? What is the solution? Feedback. How do I know that I'm getting the conversion? How do I get the conversion that I want? Not by operating at the temperature Aspen said, or by operating at the pressure that Aspen said, or by operating with the stoichiometric input relations that I calculated using first principles chemistry. Why? My catalyst has become poisoned. My flow rates are unreliable. The temperature and pressure that corresponded to those things in Aspen were calculated using models which weren't reliable even when we fit them to the data that they were used to get the models in the first place. Right? So the one thing we absolutely know is that the answer, the correct answer on site, is not the one that comes out of Aspen. So what's the final word? The actual, how do I know what conversion I'm getting? I measure the conversion. I measure the actual stuff coming out of my reactor. And if I'm not getting the conversion that I wanted, I make changes to the operating conditions on the site. And how do I do that? By using feedback control, by measuring that thing and saying, well, if the conversion is too low, I must increase the amount of the limiting reagent that I feed. Right? And PS, like, you would be silly to feed the correct stoichiometric ratio in the first place, right? Because you always feed more of the one, right? Because you'd be silly to just feed exactly enough. Like maybe you didn't get that calculation right. And now like you've got the wrong limiting reagent. So you always feed more of the one. And you play around with the limiting one, right? That's how you actually do the thing. So all of those lessons taken together, I want you, those flags are not in the textbook. This piece of lecture here is, I think, like not even for exam, you know, like I'm not going to ask specifically a question about this, but it is the most important thing that you have to armor your mind against when you read through this section, because the feed forward section of the book makes feed forward look amazing. It makes it look like 10 times better than feedback. But it's not. And I'm just here to wave those little flags to say, like, just be aware it's going to be really beguiling, this idea of like, oh, I just use my model equations, I trust my model equations, everything makes a great deal of sense, and then I'll get great control. When the actual way to get good control is to use feedback correctly and to understand that you're going to have different things on site than you could ever calculate offline.